Dr. Vijay as a person to deliver this lecture. Thank you.
Yeah, thank you for a nice invitation, Dr. Kavita, and it's a good. I'm really privileged by such invitation from SNS College, and I'm really always happy to be part of Coimbatore because I grown up there during my college days. So it's like my second hometown always. So whenever I visit Coimbatore or someone give me invitation from Coimbatore, I really happy in a double manner. Yeah, and hope everyone hears me clearly, right? So we can go for bilingual or English. Oh, are you hearing me? Shall I continue?
Yes, sir.
Yeah, okay. Yeah, sorry. As there was a deep silence, I was worrying that there is some problem with connection. Okay. So I continue with my talk today. Very good morning to all. Of course, it's good morning to me and good afternoon to you. It's almost 8 o'clock for me now. Yeah. Today's topic is nanomaterials for energy conversion and storage. As a material scientist, I mostly work with material synthesis and characterization. I don't usually work with application part. Of course, my collaboration team or my students used to work on those area. Nowadays I'm more narrow down my research category towards electron microscopy, even within material characterization. So I'm a purely an electron microscopist. I don't do any other work than microscopy. Of course, we do have some synthesis experiments and characterization of those nanoparticles or nanomaterials in the two-dimensional materials for energy applications, in particular energy conversion and storage, like lithium batteries or supercapacitor and solar cells. So we have very good publications recently. Even last month, we had a publication in collaboration with CIT in scientific Nature publications in perovskite material for solar cell applications. Apart from that, I usually work with carbon nanotubes and two-dimensional materials, in particular transition metal dichalcogenides. So what I plan today is I restrict my topic within carbon nanotubes and two-dimensional materials. What we work on those things, what we studied and why we studied, and what are the application part of those materials. So it's purely a carbon-based material and two-dimensional transition metal dichalcogenides. In particular, it's molybdenum disulphide. So with this short introduction, I will jump into the slides. So the nanomaterials, when the topic is nanomaterials, we need to cover what's a nano, right? A nanometer is 1,000 millionth of a meter, and the study on the structure and materials on the scale of nanometer is a nanoscience. So the image is given to compare what is macro, what is micro, and what is nano. Like what we are dealing now is with nano and angstrom level scale, which is far, far down to what we are seeing in our day-to-day regular life. So if you compare a person with 2 billion nanometer to 0.1 nanometer of hydrogen atom, it's a wide and vast difference. So in particular, these things, like luckily as an electron microscopist, I am used to work with this nano and angstrom level particles or angstrom level imaging or detections. So I know how quick we can get with advanced technology nowadays compared to what we worked 10 years back. I started my career as an electron microscopist in Indian Institute of Science as a research student before 13 years. Then because of that, I came to Norway for my PhD. So I started my career with carbon black nanoparticles, carbon nanotubes, then jump on to two-dimensional materials. So this is how I was grown up. So with this introduction, as I was repeatedly telling carbon nanotubes, the carbon nanotubes have a very strong historical connection to our Chera kingdom, or too prominently we can say it's Tamil Nadu. So this is a wood steel structure which have historical root before 400 BC or 600 BC. So with this wood steel, this is an image taken from Damascus, maybe near Syria. So they found carbon nanotubes within the steel structure. So they wonder how it comes, because in the world, they never found any carbon nanostructures within the steel, even though the steel is produced with combined with iron and carbon. But nowhere they found carbon nanotubes. Only this type of wood steel structure have special kind of carbon nanotubes when they dissolve the steel structure to find the internal particles or internal tubes. So finally, they've concluded, even in Nature publication, it came as a news story. The carbon nanotube may have given swords of Damascus their age. So they found the root and they came to locate these type of wood steels, or probably came from Tamil Nadu, or previously it was in Chera Kingdom. So maybe South India. Those things are mentioned even in Wikipedia or Nature publications or in the dictionaries. So it's proven one. So wood steel is a crucible steel characterized by a pattern of bands and high carbon content. So whenever there is a high carbon content, when it mixes with these metals, like a transition metals like iron or nickel or cobalt, due to high temperature or high pressure in nature, the transformation of carbon occurs to the nanostructures or more graphitized structures. So I'm more happy to give this slide or talk about this because my PhD was about the carbon nanotubes. I was working with carbon nanotube phase transformation from carbon black amorphous nanoparticles to make it graphitized one. So it's more or less personally connected to me for my PhD research and personally connected to our historical roots, personally connected to our Coimbatore region. So that's why I want to show this slide, wood, steel, and carbon nanotubes. So with this, I will move on to the topic. So with carbon nanostructures, we have wide variety of choices, like from 0-dimensional fullerene, 1-dimensional nanowires, or 1-dimensional tubes again, and 2-dimensional graphene sheet. So recently, with these things, they also try to bring in 3-dimensional hybrid structures. For example, maybe with mesoporous composite electrode or microporous composite electrode, or carbon-coated nanoplates with hybrid nanoparticles or core shell particles into the carbon nanotubes. It makes dimensional things. So there are advanced in carbon nanostructures, even within 0-dimensional, 1-dimensional, 2 or 3-dimensional. There are more and more new materials are synthesized or produced in a laboratory in order to test those particles or those materials into different applications. It includes energy applications. So this slides, it shows 0-dimensional, 1-dimensional, 2-dimensional carbon nanostructures, which is more particularly useful in energy applications. Even though the carbon nanostructure really have wide applications, this slide shows these graphene-based composites or carbon-coated nanoplates are mostly used only in energy applications. With the nanoporous carbon, as I told you, there are applications apart from energies, but when we restrict only to the energy devices, there are batteries, supercapacitor, fuel cells, or oxygen reduction reaction, or hydrogen evaluation reaction, or there are more application into photocatalysis. And the most useful part out of energy devices is drug delivery, which is useful in bio and medical things. So the nanocarbon, as it is, can be used in all such applications. However, also can be functionalized or doped, or the phase transformation can be done as like me. So the carbon can be tuned its property with everything, like function, either through chemical or surface modification or through phase transformation. Completely, it gives a different results than its original structures. So we can use it as a playing tool. We can do whatever we need, whatever we can focus, whatever we can aim for with carbon structures. That's a specialty of carbon. And the second is it's really available, abundant in this world, and it's cheap. So it's really a carbon material. Of course, our body is also made up of carbons, right? So it's carbon is everything. So why not in energy devices, right? So I will move to the slides, which shows what I did with carbon nanoparticles. So what I did is a solid phase transformation. I have used a different iron and nickel combination to make it transform into amorphous, into graphitized nanostructures with different metallic structures, like from nanotubes with the top edge metal coated nanotubes, or within like a chain locked like here it's like a nano chains, and there are some open edge carbon nanotubes. Here it's top edge metal decorated carbon nanotubes. So these things are possible with phase transformation, what I did. So this can be used for different application. Of course, when I was doing PhD, I was restricted my research to material synthesis and characterization. As I told you, I'm completely now down to characterization. So I don't even synthesize anything now. But these are the things which I synthesize in my earlier days. So this is one of the like phase transformation I did using microwave irradiation. The first one is amorphous carbon nanoparticles, which can be transferred to nanosticks, which is more amorphous, and nanoballs with different microwave irradiation treatment, maybe with different timings. So these nanoballs becomes now the hybrid 3-dimensional. After it can be decorated with some metal particles or metal oxide particles, or metal oxide. Even nano rods can be added with metal dopant later on. So it can be used in supercapacitor in later days. When I was working, I just tried a synthesis with different microwave treatment and get different structures, like from particles to quantum dots to nano sticks in amorphous form and nano balls. So I have tried wide combination to get all these structures. Then I have used most of my time also in functionalization of carbon black nanoparticles and functionalization of carbon nanotubes. Because, for example, in fuel cells, the platinum electrode can be enhanced with its capacity using carbon attachment. So the carbon and platinum should be attached. So the carbon should be functionalized to get platinum nanoparticles on its side wall. So the functionalization of carbon structure is more important. I have used organic acid at the time when most of them are using hydrochloric acid or nitric acid. So that makes more stable carbon structures even after functionalization treatment. Nowadays, there are more polymer chain addition or organic complex structures even can be added to carbon nanostructures in order to functionalize it. And there are more region-wise functionalization is possible in this advanced research world. So when I was doing, I was concentrating on functionalization of carbon towards fuel cell electrode application. So these are the things are possible with carbon structures. Like this, even sulfuric acid or potassium manganate can be used to zip it or to make different zigzag orientation or to make it armchair orientation in order to make, for example, here which is shown platinum carbon electrode in the fuel cell chamber. So these are the possible things with carbon functionalization to make more efficient like platinum electrode, or even ruthenium electrode, or sometimes nowadays used ruthenium oxide electrode in plus carbon. So these are the things are possible with carbon functionalization. Of course, it's not only restricted to one fuel cell. For any proton exchange membrane or direct methanol or alkaline, phosphoric acid, or molten carbonate, or solid oxide. In all the fuel cells, in everywhere when there is a need of electrode, the carbon can be added as a nanotube, or even the graphene or graphite oxide, graphene oxide, together with these metal nanoparticles or metal dopants. So everywhere it's used. And solid oxide fuel cell, as it is, you see, it's work at 1,000 degree or more, or related to that higher temperature. There are possible corrosion during the operation, most particularly in the region of interconnection stainless steel. So nowadays, recently I was working with solid oxide fuel cell group only towards studying corrosion on interconnects between the chambers, and I'm more restricted towards my work in electron microscopy. I do a lot of studies on these materials after 3,000 hours of operation, after 5,000 hours of operation, after 10,000 hours of operation, and study how the material is degraded, or is it possible to withstand at this temperature with different stainless steel composition. And sometimes our group also make a cerium coating or cobalt coating. Nowadays they started to use copper coating onto the stainless steel to study or to make it more stable interconnect environment in solid oxide fuel cell. So these are the fuel cell. I started with carbon, and even I just wanted to convey with solid oxide fuel cell, because as I am working more closely with solid oxide fuel cell, there is another part apart from the electrode. There is another part with interconnect need to be more stable attached to that environment. So we are working on that one nowadays. So with this, I move on to two-dimensional material, which is my second most related research work in my career. Two-dimensional in the sense we can call it as either as a graphite sheet. As you know, the graphite is arranged as an hexagonal turbostratic arrangement. If you peel out a single carbon layer, then it's a single graphene. More related to the carbon 6 hexagonal honeycomb structures is hydrogen boron nitrate. Boron nitrate, and that's a hexagonal shaped. So these are the two-dimensional material which known earlier days and applicable in many environment. But recent 10 or 15 years, there are new two-dimensional materials started to arise. It means it's already there, but the researchers have started to peel off two-dimensional, a single layer structure, as like graphene was peeled off from the graphite. So then new two-dimensional materials like a transition metal dichalcogenides, metal oxide frameworks, mexins like titanium carbides, or even the metal two-dimensional or metal oxides, two-dimensional, or phosphorine can be made into two-dimensional layered structures. So these are already a layered structure, so you can just peel off a single atomic column layer. So the nano is now down to single two-dimensional, a single atomic layered material. So we were extensively worked on these type of materials, in particular two-dimensional, in particular molybdenum disulphide. So there are quite many applications as like in carbon. So it's maybe a replacement for silicon era and also for the carbon era. So it can be replaced everywhere. And even this two-dimensional transition metal dichalcogenide structures can be formed as like hybrid carbon structures together, make enhanced capacity in energy storage and electronic devices in particular. So with these two-dimensional materials towards electronic devices, we have studied the growth of these two-dimensional materials. We have also studied how the defects arise and how the defects exist with the different synthesis parameter. So it can be helpful when it is applicable in FET, field effect transistor, or in other hydrogen evolution reaction with different chemical nature of the material after it have defects. So we wanted to study the defects. So when I was doing my postdoc in China, Zhejiang University, my group was working on before that, as I told you, these slides are more closely related as like two-dimensional materials in supercapacitor, battery, solar cell, hydrogen evolution. There's an extra slide. So there are possibility to grow molybdenum disulfide single layer through three different approaches, either mechanical exfoliation. The mechanical exfoliation is from the zinc crystal, which is just like using a scotch tape in our regular laboratory or in a desk. You try with different like many times, just peel off the layer, try to get into the scotch tapes, change the scotch tapes, and add those layers to silicon dioxide or any other layer, any other substrate. That's possible. This was famous after graphene was exfoliated from graphite, and even those guys got Nobel Prize in 2010 for this mechanical exfoliation using scotch tape and try to get single layer of graphene. As like even molybdenum disulfide or any other transition metal dichalcogenides can be exfoliated, like just a single atomic layer can be exfoliated. And second possibility of synthesis is chemical vapor deposition. Of course, we can use molybdenum trioxide for MOS2 synthesis or tungsten trioxide for WS2 synthesis. So when molybdenum trioxide substrate is here, together with sulfurization, it becomes a single atomic layer of MOS2. So third possibility is molybdenum disulfide powders, which is through physical vapor deposition with a high heating zone, can get monolayer of MOS2 in a substrate. So we wanted to study what are the defects possibility or defects arise when we use three different deposition techniques. So our group also studied exploring atomic defects in molybdenum. Of course, I just joined the group when this paper was going on. So this is our starting point of research in Chinese group when I started my career. So this paper published in Nature Communication, of course, they explored atomic defects, like comparing mechanical exfoliation, physical vapor deposition, chemical vapor deposition. So they found these are the defects, which means here these red squares or red circles which point out extra atoms because as like in 6 hexagonal honeycomb structures, 3 must be molybdenum and 3 must be sulfur alternatively should be placed. But here, if you see, instead of alternative sulfur, there is another molybdenum atom. So extra molybdenum atom comes from mechanical exfoliation and CVD growth. But in PVD, they found a sulfur vacancy instead of an molybdenum addition. So the vacancy is more in physical vapor deposition and in anti-site molybdenum instead of there is MO. Instead of 2 sulfur atom, there's a single molybdenum atom. Instead of 2 sulfur atom, there are 2 molybdenum atom or the vacancy here. So these are the different possibilities with they found through experimental simulation and DFT calculations. Why this needed? This is needed to place the molybdenum disulfide 2D materials in field effect transistor. So if you want to know the defects, because the defect makes like it makes a scattering center of charge carriers at some point. So we want to know how dense these defects are, or for a magnetic devices applications, we want to know how the local magnetic moment distribution is possible with defect introduction or new add atom or new anti-site defects. So these are interrelated. So we wanted to study atomically how these defects are formed with different techniques. That's why this paper was more effective. Then we move on to, of course, I was part of this. This was published in 2-dimensional Nature publications or Nature 2D materials. So we studied even just restricted towards chemical vapor deposition, and we have studied a single atomic column with 2 nanometer or 3 nanometer, how it grows, how the defects are grown, how the edges are grown, and what are the edges, whether it is moly-based edge or sulfur-based edge, how it's further on develops when it continues to grow and forms a single layer. So we have, with the use of our ChemiStem advanced Titan FEI transmission electron microscope, we can able to identify each and single atomic columns. Even the single atomic contrast are visible here. We can easily say which the bright spots are molybdenum and dark spots are sulfur because of the atomic number. So the STEM calculates easily with different atomic number elements possess a different brightness and contrast. So we can easily locate where the molybdenum is and where the sulfur is. With this, I have extended my research. Once it is found, like these are the possible things with molybdenum disulphide CVD growth, and already our group have explored atomic defects. So I wanted to try with an addition of a new atoms. Like I wanted to introduce tungsten into molybdenum disulphide. Of course, I found monolayers. The monolayer growth was perfect. Then the EDS, it clearly says molybdenum and sulfur, so it's MOS2 monolayer, and these are the tungsten atoms located around the edges of those monolayer triangles. So we can, even with atomic resolution images, we can point out these bright spots are tungsten. If you remember, I told the bright and contrast of atomic imaging varies with atomic numbers. So the tungsten have a strong atomic number, a higher atomic number compared to molybdenum, and sulfur is very less compared to these two. So we can easily identify which is molybdenum, which is sulfur, which is tungsten. So we found the tungsten atoms are just cornered or situated only on the edges. So we also able to locate few very atomic clusters. This can be like an like initial stages of growth. So I could able to write off or understand how the initial atomic clusters are formed, and then it's transformed to the monolayer atomic structures. So these type of metal doped molybdenum disulphide are very useful in hydrogen evolution reaction or in hydrogen water splitting things, and also in oil industries where sulfur and purifications are possible. So we need to know how this dopant affecting the two-dimensional structures. So we are studying it in atomical way or atomic resolution through atomic resolution images to understand more in depth into these materials for, of course, in energy applications. I could even be able to locate just a single tungsten atom which is on the edge of say small atomic clusters of MOS2. It means once the MOS2 is formed, then the tungsten is coming in due to some reason. Then it have position only on the edges, not into the internal structures. That's why it have more are located more on the corners. Of course, there are some tungstens into the center part, but it's very rarest of rare things which we found through the thousands of atomic clusters we studied. So with this, of course, we have seen carbon nanotubes, graphene, two-dimensional materials. So these things are applicable in supercapacitors, batteries, biomass conversion, water splitting, photodegradation, solar cells, or thermoelectric conversion of fuel cells. So we'd like to know what are these things one by one. Then we will see where these materials are applicable and what are the things at least I have took part in such research collaborations. So for maybe there are more bachelor students here, so I wanted to show this. This is a lithium-ion battery which won a Nobel Prize for Chemistry in 2019, very recently, last year. So the battery is such an important things in scientific world and into the commercial applications. So as you know, from the beginning or from your school days, you have studied these type of batteries, how it works without load. The overheating is possible, so there is a possibility for explosion. So we need to connect and load. So there is a probable possibility of ionic exchange through the electrolyte, and there are some separator here, like maybe a polymer membrane, which have more porous nature in order for ion to be permitted. So the ion movement and the electron movement makes the load into the current flow. That's a basic phenomena behind battery. So with the lithium-ion battery, he found, like a Stanley Whittingham, he started with the structure of lithium-ion battery from a anode and cathode. These are the lithium ions which permeated through the separator, through the electrolytes, and used cathode as a titanium disulphide. It was first achieved with 2 voltage, 2 volt. Then he transformed metal sulfide into metal oxide, ion good enough. He used the same system, and he found with the change of metal sulfide to metal oxide, he got 4 volt through this load. He have used also cobalt oxide instead of titanium. Then there is Chinese scientist. He have used cobalt oxide, then introduce a petroleum coke here and make a barrier. Then he make more efficient way of a commercialized way of lithium-ion battery. So this how the lithium-ion battery was transferred from ages to ages with the help of these 3 great researchers or professors. Then they were awarded Nobel Prize last year. This is the flow of schematic of lithium-ion battery, where the possibility of lithium-ion intercalation through the different interconnects. So when we use carbon structures or graphene structures here, or the 2-dimensional structures here, that makes the reason why the lithium should be efficiently intercalated to those materials when it comes to anode or cathode. That's why we wanted high surface area structures here, or high surface area nanostructures here, to get those ions to be accommodated or intercalated, we can say. So this is a charging flow diagram, and this is a discharging flow diagram. So when we come to graphene part, not only graphene is used in a lithium-ion battery, even those hybrid structures or with graphene with cavity, so it can accommodate more lithium, or with mesh-up arrangements in a 3-dimensional way, like in a flower shape or in a different shape. So there are more possibility for lithium-ion to be accommodated or intercalated. So that's why it's not strict to a single structure. It can be a varied structures with advanced development. As I told you, not only the graphene, there are molybdenum disulphide and graphene hybrid nanoparticles or nanostructures are incorporated into this anode region to get more efficient flow of capacitance. In case of supercapacitor. Also, there are possibility for, like, they just use a graphite, oxidize it, it becomes graphene oxide. With some intercalation, they used DODA. Then there are possibility for making a porous structures, so it becomes very highly porous graphene oxide. Then they used it as a anode in the lithium-ion batteries. This is one way of getting, instead of direct graphene, like oxidizing and make it more porous. So the oxidation, it means it's almost like a functionalization. So there are more like chemically open or chemically can be reactive structures. So these intercalated ions can easily come and find its own pair to make a stable nature if it is needed at some point. So there are also possibility for grow of silicon nanowire, as it is started with silicon oxide replacement or metal oxide replacement. Now they are also started to use either the semiconductor or metal oxide in such an anode together with carbon nanotubes. So this is one possibility of like combining silicon nanowire and carbon nanotubes. They have used double wall nanotube bundles instead of a single or multi-wall carbon nanotubes because of some reason. It should not hinder the incoming ions, so there should be more open space. At the same time, it should have some enhanced capability than multi-wall carbon nanotubes. So as I told you, there is a second possibility of combining these two materials, like two-dimensional MOS2 or three-dimensional MOS2 into the carbon, making a nanocomposite. It can be a zero-dimensional or one-dimensional or two-dimensional or three-dimensional. Can be used like top-to-down approach or bottom-up, like in CVD or wet chemical approach, to make a three-dimensional hybrid structure of carbon and MOS2 for anode application in lithium-ion battery. This is one possibility. There is another possibility with they make a graphene first, then they added a MOS2 nanosheet later on with graphene, then they added MOS2 nanoparticles. At some point, some researchers have used zinc oxide, or some researchers have used gold nanoparticles. Some researchers have come across with silver nanoparticles or platinum doping, and somewhere I have even come across with nanotubes, then the metal oxide, then the metal nanoparticles of different metals. So these are the wide possible options to get lithium-ion battery more efficient compared to the previous just carbon structures or the hybrid structures. So the researchers are keep on getting new materials or trying to form a new material with different dopants or with different hybrid layers, to make efficient anode. This can also be used in sodium-ion batteries instead of lithium-ion batteries by using different combinations. Like here, the sodium is intercalated instead of lithium, and this is like 2H and 1T is the different phases of MOS2. So even as like we also try to synthesize a different phase of MOS2 within a single carbon or single atomic layer to fit into such applications. Of course, we didn't succeed in making such a single, like a double phases within a single atomic layer, but these are another option. So because the single 1T phases of MOS2 can access a pathway here for sodium ion to be travel. So these are the different phases possible instead of making hybrid structures. The internally hybrid structure by making a different phases of same material. So that's also widely in research nowadays. As I told you, I never succeeded in achieving 1T itself because it's very hard. Even achieving a tungsten or cobalt or nickel doped into molybdenum disulphide layer, it's really very hard. Somehow I tried it and I got tungsten dope and MOS2. That's why I put that in scientific reports in the Nature publications. So that's how we need to get new materials in a new thinking, new way of thinking to make more efficient into energy applications. So these are like one examples how we transform 2H into 1T in a sodium ion intercalation. Then the sodium ion can easily travel there. Yeah, this is from my colleague. Of course, I am not a co-author, but I was acknowledged for the discussion and manuscript writing of this paper. So far, we have seen anode material for lithium-ion battery by using carbon or molybdenum disulphide hybrid. But this is for cathode material, like making a lithium iron phosphate to make it as a cathode material in lithium-ion battery. This particular work, my colleague have concentrated in developing beta phases of lithium iron phosphate. So with the beta phases, it cannot withstand highly efficient. It cannot be highly efficient. So this need to be transformed to alpha phase. Before that, he wanted to protect this hybrid nature. In alpha phase, we cannot directly synthesize. So we want to synthesize in beta phase, then transform to alpha phase. So what we did is he synthesized simply through solvothermal method. Then even he has made some carbon coating here. Then the carbon coated beta phase lithium iron phosphate is ready. Then he did some annealing. Then he made alpha phase of lithium iron phosphate through the phase transformation process in annealing without any other chemical reagent. So the structure is protected, but the phase is transformed. So this is how this is like another way of getting a phase transformation, as like I told you in molybdenum disulphide transforming from one phase to another phase. We can also do it here in lithium cathode materials, transforming from one phase to another phase to enhance the risk. Then yeah, this is high resolution TM image. Of course, I have worked in early days to obtain such nice lithium iron phosphate high resolution TM image to find the crystal orientation, and with the structures as it is atomic resolution images, we can even combine with crystal maker to make the same crystal repetitions or replications, and can found in which direction it is grown, like length direction is 001. This is an Fourier half Fourier transform. It's like a diffraction pattern, so we can easily calculate the length direction and other phases what is located. So this is from beta phase, and when we change to alpha phase, there is a possibility of change its length direction, even like in 100, here it's 020, and we try to identify these phases and make like again a crystal maker. Then even we used FFT to make sure this is arranged in this manner. So this is a material we used to study for like a cathode application in lithium ion battery. So those carbon materials or MOS2 can also be used in supercapacitors. The supercapacitor is like a double layer electrochemical layer, or double layer capacitor we can call. In lithium ion battery, there are anodes and cathodes. Here it's same anodes and cathodes, but only the charge building is different in process. Here it's ionic moment. That's the difference here. And the function is more or less similar. So this is one possibility of using multi-wall carbon nanotubes in a stacking arrangement with, for example, the gold nanoparticles are attached here in the MnO2. MnO2 it's doped on attached to carbon nanotubes. So above that there is a gold layer which acts as like because of the contact resistance, this gold layer is introduced to reduce those contact resistance. So that's why I said in addition to metal oxide with carbon nanotube, there are newly added metal nanoparticles as a dopant on the edges, or like a layer here which is shown in this image. So this is a supercapacitor application of multi-wall carbon nanotubes. Yes, I wanted to show you because I was working in this industry to get carbon nanocarbon particles from a decomposition of methane. So the hydrogen can be extracted from or get from methane decomposition, and the carbon can be used for different application, as like me working in phase transformation and surface functionalization. There is another possibility like getting hydrogen for electricity applications. So this is one way. The second way is hydrogen evolution reaction, as like in what we seen in battery and lithium ion batteries and supercapacitor. There's a cathode and anode. Here the water splitting is occurring instead of chemical electrolyte. Here just water. Then there's a possibility for hydrogen and oxygen reduction here. So or hydrogen evolution reaction is possible in the cathode. So these type of approaches brings hydrogen production, can be used for green energy applications later on. So this is an studies which concentrated on hydrous ruthenium oxide and crystalline ruthenium oxide. So this is a, if you remember here, the cathode is hydrogen evolution reaction possible at this stage, and an anode, it is oxygen evolution reaction. So these were studied together with hydrous ruthenium oxide plus crystalline ruthenium, or the traditional one with iridium and platinum carbon. They wanted to replace this because these are really costlier, commercially not viable for everyone. So they wanted to go for cheap materials, and they found somehow the current density is enhanced in a low voltage compared to platinum. So somehow they are successful in replacing the traditional platinum carbon into ruthenium oxide alone without any need of carbon materials. So this is one new way of replacing carbon into oxides. So this is why I wanted to show, like, even as you might have remembered, I have tried tungsten doping with MOS2. Of course, my original plan was to get cobalt doping into MOS2 to make it into He or activity, like a hydrogen evolution reaction. But it's very hard. So I tried with tungsten because tungsten S2, like a tungsten WS2, tungsten disulphide is also a layered material, and the molybdenum atom can possibly replace, like tungsten is possibly replaced with molybdenum site. So the anti-site of molybdenum is possible. That's why I tried with tungsten instead of cobalt. Of course, I was successful with tungsten. Then I couldn't able to get cobalt enhanced or cobalt doped MOS2 and single layer or two-dimensional layers. You might have wondered how these guys achieved. Of course, this is a theoretical paper, so I don't think recently they still achieved with practical cobalt doped MOS2. There are some papers, but not a repetitively success. So achieving metal doped MOS2 is going on recently in many research laboratory to get into the hydrogen evolution reaction. Otherwise, we have to go only with MOS2. As of now, that's a possible thing we have in hand. So these are the different materials and different applications in energy devices. So I wanted to show very quick few slides with solar cells, because these are the recent publications which I made it with CIT through a PhD student in physics department, Coimbatore Institute of Technology, Selvakumar. He worked even in Norway as like a visiting student. Of course, almost everyone in physics department in CIT can come to Norway for 3 months during their PhD period. Like every year, they can come at least once or twice. So this is like partly a collaborative work from Norway, Sweden, and CIT Coimbatore. So this paper is published in Material Research Bulletin. He have synthesized a perovskite with different molar ratio of these things. Then he even like made a multi-junction solar cells, and have studied the fill factor and efficiency with different molar ratio of reactant used for perovskite. So this is one paper we published in solar cell, and the second one we have used zinc oxide nano flakes, which synthesize from like green synthesis, we can say from albizo amaro leaf, and we get green synthesized flake like zinc oxide like this. Then zinc oxide and titanium dioxide is combined to make it as a whole transport layer in the multi-junction solar cell, in a perovskite solar cell. So means the titanium dioxide's limitations are overcome by combining zinc oxide nanostructures. That's why we introduced this one in a whole transport layer region. So it enhances the whole transport, electron transport layer, So it enhances the electron transport because of the combined zinc oxide and titanium dioxide layer in this type of arrangement, like in a multi-junction arrangement. This is a recent publication in RSC, and of course we have another publication just last month published in Scientific Reports, again in Nature. That's also wonderfully done by the same PhD student Selvakumar in CIT. So I didn't have such accepted version, so I didn't want to show here. But we have a very wonderful publication recently from Coimbatore. Even though I am just material guy, I have such a collaboration network to work together to get energy applications. So these are our work on perovskite solar cells. So this is to show how he have made the different layers, like drop casting technique, and make a fully fledged perovskite solar cell with mixed halide. So the device performance also studied and seen the titanium zinc oxide bilayer, the electron transport layer, have some enhanced efficiency. If you see here, the efficiency is enhanced when compared to just titanium dioxide or without titanium dioxide and zinc oxide, with titanium dioxide and zinc oxide nanostructures. So this is like a fantastic work which shows improved efficiency with zinc oxide incorporation. There are papers which also used other metal oxides like tin oxides or other transition metal oxides. So this is one kind to use zinc oxide because of its band gap, which can be easily work together with titanium dioxide and enhance the electron transport efficiency. So that's in turn increased photo efficiency. So these are the works which are related to my career and related to my collaboration related to our today's topic, like nanomaterials in energy devices. So with this, I'm concluding. If you have any questions, please ask. Thanks for your kind attention for such like 1 hour. Or you can even type here because if you started to talk together, then there may be a problem. So just type here. Even I can type my mail ID. If you have questions, you can even later on ask me through my mail. This can be visible in chat box for everyone.
Hello, can you hear me, sir?
Yeah.
Yeah. Sir, on behalf of the audience, I'm asking you the questions. Dr. Selvaraj Narayanan has asked a question like, why is preparing carbon nanotubes are not so easy?
Why carbon nanotubes are so easy? Is it?
Why? Yes, sir.
No, it's actually easy because it's the carbon nanotube research is like it's now past 20 more years. It's possible with good thermal furnace. Even research was about to reduce the temperature in bringing as graphitized carbon nanotubes in my research work. I have even carried out like in a way, either using like in a beaker with 400 temperature or with microwave oven commercially available. So it's possible, but we need to work in a more appropriate way. Say, otherwise we need to laboratory where we have high efficient thermal furnace. So either you can choose that, you can choose laboratory way with the public like me who already shown synthesis in a low temperature, or I can help you if you need. If someone need in collaboration to synthesis carbon nanotubes, I'm very much happy to guide through past experience. And I can say I was working in a group during my postdoc. My professor Chun Han Jin, a student of Sumio Ijima, So Fumio Ijima, you might have heard, he was the one who discovered carbon nanotubes. So I was the part of student group. So I have more experience in carbon nanotube synthesis. I'm really like to help you if you need in cases like some collaboration work.
Okay, thank you, sir. Dr. Paulson has asked, kindly explain which kind of impacts and modifications are to be introduced when adding dopants in raw graphene oxide.
Can you repeat the question?
Kindly explain what kind of impacts and modifications are to be introduced when adding dopants in raw graphene oxide.
In raw graphene oxide.
Yes, sir.
Okay, so the dopant or functionalization always intended for two things. One is like functionalization introduces defects, so that there are dangling bond or chemically active bonds to get more additional inputs from the system, either defects or through the it enhances the carrier mobility or sometimes in electron mobility. It depends on the system where we are doing. So I think I have answered it. Is it?
Yes. So the question, is there any connection between temperature and defects in 2D materials? The question is from Dr. M.R. Meera. Is there any connection?
There must be a difference, but we didn't study it. At least we have concentrated on different synthesis techniques and studied widely and more into atomical way of two-dimensional materials. But I have never worked on temperature-based things. But certainly there are possibilities, of course.
And from a question from Dr. Amudha Raj, in dichalconogenides, rather than molybdenum sulfide, which is the one used most frequently for application purpose?
Sorry, can you repeat the question again?
Rather than molybdenum sulfide,
Yeah.
in dichalconogenides, rather than molybdenum sulfide, which is the one is used most frequently for application purpose. Other than molybdenum sulfide, they are asking.
Yeah. Actually, the molybdenum disulphide we are going on because it's very easy to synthesize compared to other dichalcogenides. Apart from that, there are possibility for molybdenum tellurides and molybdenum selenides and even sulfur doped molybdenum selenides or selenide doped molybdenum sulfides. We have tried, at least our students have tried different combination of this. We never enter into WS2. Actually, I was about to synthesize WS2, but accidentally I synthesized W doped MOS2. That's a different story. But we can use these type of two-dimensional materials. But only thing is to synthesize, it's very hard. To get stabilized formation is very hard.
Hello.
Yeah.
The same related questions is become form in live chat. Which is the best method to prepare MOS2 nanomaterials?
Nanomaterials or two-dimensional materials?
Yeah, especially in MOS2.
Are you intended for two-dimensional?
Two-dimensional.
Yeah, I can say CVD is one of the good thing because we have tried a lot with PVD, but not succeeded always. But CVD, once you stabilize the system, it's very it can be repetitively produced. Or the simple way is Scotch tap.
Okay. Then one more question. Karthikeyan Shanmugam will be asked. Zinc oxide, tin oxide materials used in reducing the size of the nanoparticles.
No, I didn't get the question. Zinc oxide and titanium dioxide is used.
Used in reduce the size of the nanoparticle to the fabrications.
No, I am not clear with the question. I understand the question, but I'm not clear what like where you like Can you make more precise?
Sir, Vijay sir, sorry to interrupt you. Kindly switch your video mode.
Oh, okay. Yeah, just a minute. Where it is. Yep.
And like, how is polymer converted into nanomaterial? Hello?
Converted to nanomaterial.
Yes, sir.
No, it's like the carbon can be transferred into any kind of phase transformation. At least I never worked with such a polymers, but I have come across some articles, but I don't have personal experience in working on that. My video is not clear. I don't know why.
Yes, sir. Hello?
Yes. So, but for
Can you hear me, sir?
Yeah, I'm hearing you, but I have returned my mail ID. Anyone can contact me if you have more questions or like
Okay, sir. Okay, sure.
detailed answers or detailed discussions can be possible in mail or through my phone instead of here.
Okay, sir. Okay, sure.
Hello.
Vijay, sir. சொல்லுங்க.
முடிச்சாரா? Thank you, sir. Hello.
Yes, சொல்லுங்க sir.
Thank you, sir. Last week நீங்க ஒரு செமினார் கொடுத்திருந்தீங்க இல்லையா? Webinar that I also attended.
Okay, okay.
Question கேட்டாங்க. Nano mask, bio.
Yes, bioimaging, yes.
Both are very good interactions, sir. Thank you very much for your accepting in our college acknowledgement. I am the one of the faculty of SNS College of Technology.
Oh, okay. Thank you, sir. Thank you.
Me and myself and Kavita also to be, Dr. Kavita ma'am also to be organized this.
Okay.
Thank you for your acceptance. நான் அன்னைக்கே கேட்டேன் உங்ககிட்ட, சார் இது எனக்கு பண்ண முடியுமா அப்படின்னு, பட் the ma'am is done it.
Yeah. Thanks for your invitation.
Thank you, sir.
I think Vijay sir and ma'am, we are running out of time. Can we close?
Okay, sir.
Yeah.
Okay, sir.
Yeah.
Thank you so much,
Thank
sir.
you.
Yeah, thanks for your time.
Thank you. Bye.
Thank you, sir. Bye, sir.
Thank you, sir.